Have a directed graph, a dependence graph. Like, for example, the graph representing the courses in your in a certain curriculum, or the courses required for earning a degree. For example, in computer science, you have programming 1 and programming 2. And programming 2, and normally you have a data structures course, and data structures. Usually the the prerequisite for data structures is a discrete math course, and then data structures is a prerequisite for other courses. Like, for example, software engineering, operating systems, algorithms, and you may have, for example, a course that has all of these courses as a prerequisite. For example, some elective course, say security course, that has, say, operating systems and algorithms as a prerequisites. Okay, so this is just an example. So this is a directed graph. It's a dependence graph. Now the question is, we need to come up with an order of these vertices that satisfies these dependencies. So for example, if you come up with an order like programming 1, programming 2, then discrete math, then data structures, then operating systems, then software engineering, then algorithms, then security, this will be a valid order. But if you do something like programming 1, programming 2, data structures, this is an invalid order because it does not honor which requirement? Yeah, it doesn't satisfy the dependency of data structures on discrete math. So there is a dependency that is not satisfied here. So basically, topological sort is finding an ordering of the vertices such that whenever there is an edge from x to y, x appears before y. So find, or given a directed graph, given a directed graph, find an ordering of the vertices such that if there is an edge from x to y, x appears before y. In this order. Okay. Now, in order for this problem to be solvable, we cannot have cycles in the graph. So the graph has to be acyclic, right? Because if we put a cycle in the graph, like for example, this. So we are saying that these courses are prerequisites for algorithms, but algorithms is a prerequisite for programming 1. So this is impossible. These dependencies are impossible to satisfy. When you have circular dependencies, these will be impossible to satisfy, and the problem is not solvable, or the problem is not defined. It doesn't make sense to define a problem, the topological sorting problem, on a cyclic graph. So that's why, given a directed acyclic graph, directed acyclic graph, or usually we use the acronym DAG, find an ordering of the vertices such that if there is an edge from x to y, then x appears before y. Okay, now let's think of an algorithm for doing this. So can you think of an algorithm for doing this? Now, we need an algorithm, not just a way of solving this example on the board. So we need a general procedure, a procedure that will work all the time. It will take any graph and it will come up with a topological sort. So remember, keep in mind that the graph is represented as an adjacency list. So our graph here is going to look like this. Programming 1, programming 2, discrete math, meaning of S, oh, did I miss anything? Yeah. So for programming 1, the neighbors are programming 2. For programming 2, the neighbors are data structures. For data structures, you have 3 neighbors, SE and OS and algorithms. For discrete math, we have data structures. I don't think I have to show all of them. So you get the idea. So this is the adjacency list. Now, if I give you this adjacency list, I give you an adjacency list like this. How do you come up with an ordering of the vertices? How do you write a program that takes this adjacency list as input and gives you a valid order of the vertices as output? Well, if we think intuitively, then it looks like the order must start with either programming 1 or discrete math, right? Because these vertices do not have any dependencies. So it must start with one of these 2. But now how do I identify these two vertices using this adjacency list representation? So if I give you this adjacency list, how do you identify programming 1 and discrete math?
There is no incoming connection for programming 1 and discrete.
Okay, so there is no incoming edge, which means that
They are sources.
okay. So given this adjacency list representation, how do I identify these? Write a program that takes this adjacency list and tells you that programming 1 and DM are the ones that you can start with.
We can calculate the incoming connections and
How?
Like we can like each child we can increment the counter by 1. Like programming 1 has 1 child, programming 2, so we can increment 1 count by 1. So like this we can calculate all the child and their counts, and the node which has like 0 count, those are the
Yes, okay. So we can use the adjacency list to count for each vertex the number of vertices that it depends on, or the incoming edges. So the number of incoming edges, or you can think of it as the dependencies. So for example, the dependence count for programming 1 is 0. Dependence count for the discrete math is 0. Dependence count for this is 1. Dependent count for data structures is 2. There are 2 incoming edges. for this, it's 1 equals 1, and this is dependence count equals 2. Okay? Now, how do we calculate this? So we traverse the adjacency lists and count how many times each of these vertices appears in an adjacency list. So for example, for data structures, it appears here and here. It appears twice. Because it appears twice, so we count the number of appearances of data structures. That gives us the dependent count. Well, then, we can identify a vertex with a dependence count of 0, and we start with that. So in this case, we can say, OK, programming 1 is something that we can start with. Then, when programming 1 is done, now this dependence of programming 2 is satisfied. So now we can say, OK, we can decrement the dependence count, and this is now 0. After we put programming 1, this dependence became 0. So now we have on the list of vertices that are ready that we can pick now. We can pick either discrete math or programming 2 at this point, right? Because they both now have 0. So let me pick programming 1, programming 2. Now if I pick programming 2, this is going to satisfy one of the dependencies for ds. So now what should the dependence count for ds become?
1.
It becomes 1. So what does it mean? It means that ds depends on 2 other vertices. One of the dependencies has been satisfied because we have already placed programming 2 in the order. We are still waiting for this. All right? So now, is data structures ready to go? No, it's not. What's the only vertex that is ready to go?
Discrete.
Yeah, discrete math. So we do discrete math now. Now when we do discrete math, this is going to further decrement this to 0. Now data structures is ready to go. But then it's going to decrement all of these to 0, 0, 0. So now we can pick any one of these 3. So we can do software engineering. And then it's not going to decrement anything because it has no dependence. Then we do OS. OS is going to decrement the dependence count of this to 1. So now, what's our only choice at this point? Algorithms. And then we have, this is going to decrement this to 0 now. The security course is ready to go. Okay. So this dependence count thing is the key idea in finding a topological sort. So now let's translate this into code and analyze it. Okay, so we can do. Now, how do we translate this into code? First of all, we have to find the dependence counts. So let's call it topological sort of G. So first for each. Now, in order to compute the dependence count, we first have to initialize the dependent count of every vertex to 0. So for each vertex u in G, set u dot dependence count to 0. Just initialize them all to 0. Then, for each U and G. Now we need to go through the adjacency list of U for each vertex or for each neighbor V of U. What do we do? What do we need to do based on what on this description? We're trying to calculate the dependence count, which is the number of occurrences of each vertex in this list here. So what should we do? So just increment the dependence count. So U dot depth count plus plus. So we are counting how many times it appears here. So we're going through all of these lists and we are counting how many times it appears here. So then we will pick a vertex with dependent count of 0 and we put it in the list. So now create a list, a ready list R and a solution list S. So now every vertex with dependence count of 0, we put it in the ready list. So for each vertex U and G, if U dot depth count equals 0, so we put R dot add to head or add to tail, it doesn't matter, of U. So we put it in the ready list. So all of this, all what we have done is to just count the dependent count, calculate the dependent count for every vertex, and identify the vertices with the dependence count of 0 and put them in the ready list. Now, the algorithm is going to take one vertex from the ready list. So while R is not empty, we're going to take one vertex. So we're going to say U equals R dot extract head or extract tail. When we take a vertex from the ready list, should we extract head or extract tail? Or it doesn't matter? So when you have multiple options here ready, should we take programming 1 or data discrete math? It doesn't matter. So it doesn't matter whether you do extract head or extract tail. Extract head. Then what should we do? So we put it in the solution. So we extract it and we put it in the solution. So we do S dot. Now in the solution list, should we add to head or add to tail? Add to tail, because we are, so we first picked programming 1, then we picked programming 2, so we added programming 2 to the tail. So we added, so this is the first element in the list, so we added programming 2 to the tail of programming 1, then we added discrete math to the tail. So add to tail of, we add U to the tail. Then what should we do? Okay, yes, decrement the dependent count of the neighbors. Yeah, so we have to go through the neighbors then. So now for each neighbor V of U, we say, okay, V dot depth count minus minus. Or let's say, okay, depth count equals v dot depth count minus 1. Then what? There's a very important step now. So look at this. What were we doing? How does this work? So what's the important step that we're missing now? So we decremented the dependence count.
If it is equal to 0, we need to add to the ready list.
Yeah, exactly. If it's equal to 0, then we add it to the ready list. If v dot depth count equals 0, then we add it to the ready list. So then we do r dot add. It doesn't matter head or tail. Things in the ready list are not ordered. But to be consistent, we'll add it to the tail, only to be consistent, of v. And that's it. So this is the algorithm. Any questions on this? Any questions on this? So the idea is to calculate the dependence count. So we had to do all of this we had to set it to 0 first. Then we had to go through all the adjacency lists and increment the dependence count of every. Oh, I have a bug now. Oh, so I have just found a bug.
You are incrementing v dot.
Yeah, so v. So v, not u. So this is going to be v. We go through the adjacency lists and we increment. So this is an edge from u to v, right? So you have an edge like this from u to v, so you increment the depth count of v. So everything here is a v, right? So it's v dot depth count plus plus, create a ready list for each vertex in G. If the dependence count is 0, add it to the ready list. Then loop, as long as the ready list is not empty, take a vertex from the ready list, add it to the tail, then go through the neighbors and decrement their dependence count, the dependence count of the neighbor. And if the dependence count drops to 0, now this vertex becomes ready. Okay. Now what's the asymptotic complexity of this? So there are easy loops. So this loop is what? So this is v. So this is theta of v. This is another. Well, this is not v. If we look at both loops together in aggregate, what's this? This and this in aggregate.
Oh, v squared.
No, this is not v squared. So this is for each neighbor. So this alone is e. So this is e and this is v. But this is not e times v, because it's not e for every v. It's e in aggregate. So this is v and this is e in aggregate. It's not e for each v. So this is just like a DFS or a BFS. So you are going through all the lists. So this is a v and this is an e. This is v, this is e. So this is going to be O of v plus e. Okay? And this here, how many times will, for each vertex, so this is clearly O of v. This goes through the vertices. Now, how many times will the while loop get executed? The while loop. So this line here, how many times will it get executed?
R is going to be executed. The number of vertices we have.
The number of vertices, yeah. Because each vertex cannot appear more than once in the topological sort. So each vertex will appear exactly once. So this is theta of V. And in fact, all of these can be thetas if the graph is connected. So assuming that the graph is connected, then this is going to be theta. Now, here, this for loop for each neighbor, again, this is one of those loops that visits all the neighbors. So this is one of those loops that is going to visit every edge in the graph. So it's yet another loop that visits all the edges in the graph. So this line is going to be executed theta of E. Okay? So now what's the total? What's the total running time? So again, this is V. So this is, again, another V plus E. So this is E in aggregate, because this is going to visit all the edges. This is limited by the number of edges in the graph. An edge will be visited exactly once. And this is in here, a vertex will be visited exactly once. So these will give V plus E, and this is another V plus E. So the total is just V plus E. So this is a V plus E algorithm. Now everyone should be familiar with this pattern, because we have seen it in DFS and BFS. We should be familiar with this kind of loop that visits every edge in the graph. So this is E in aggregate. And it's inside a loop that does V. So we must visit each vertex. So this is a V. So we should be familiar by now with this V plus E pattern. Okay, so this is an algorithm that does topological sort, but in fact we can use DFS to calculate this much more quickly, although it will not be asymptotically quicker. It will be easier if we just use DFS. Now the idea is, if we look at this graph, if we do DFS, and so let's do DFS and see what we can do. Okay, so we have good 10 minutes. If we do DFS, let's suppose that we started from this. So this is going to be number 1. We go to this. This is number 2. Then it has only one neighbor, so this is number 3. And this has 2 neighbors. Let's say we went to this 4. Now we have to return, because this doesn't have any neighbors. So now this is 4/5. Now what does this tell us in terms of topological sort about this SE? Where can we put it in the order? Where can we safely put it and know that that order will not be incorrect? That will be certainly valid for SE. Where can we place it?
At the very end.
At the very end. Why?
Because nothing is dependent upon it. So if you put it at the very end, it's never going to affect anything.
Exactly. Yeah. So if we put SE at the very end, we know for sure that nothing is dependent on it. So we'll just put SE at the end. So whenever we finish a node in DFS, we know that we can put it at the end. Because when we finish it, it either doesn't have any dependence, or all of its dependents have been finished already. So we will see an example of the other case in a minute. So now we go back to DS. Can we finish it?
No.
No, we cannot finish it. We'll go to OS and give it number 6. Then we'll go to the neighbor, and this is number 7. Now we finish this because it doesn't have any neighbors, so number 8. So we finish it, we put it at the end. So now we can safely put this at the end. because we know that there is nothing that depends on it. Now we go back to OS. So this is number 9. So now we can safely finish the OS. So we finished it, so we can put it. Now OS has some neighbors, but one of the important characteristics of DFS is that whenever we finish a vertex, we know that we have already finished all of its dependents. Right? You can't finish it before finishing all of its dependents. That's one of the most important characteristics of DFS. So we can safely put OS now, because we know that yes, it does have dependents, but we are certain that all of its dependents have been finished already. So we put OS. Then we go back to data structures, and we have to visit this neighbor first. So this is number 10. Can we put it now? No. It's not. We only put it when we finish it. Now, we look at the neighbors, we realize that this neighbor has been finished. So now it's time to finish it. So this is 11. So now we can safely put algorithms. Then when we go to data structures, now it's time to finish data structures. And we are finishing this, and we are certain that we have finished everything that is dependent on it. So we can safely put it on top of algorithms. And this is, are the numbers right? Yeah. Did we skip any numbers? 3, 4, 5, 6, 7, 8, 9, 10, 11. No problem. OK. So now we go back to this and finish it. So we put programming 2. And then we go back to this and finish it. 14, we put programming 1. And now are we done? No, we have to start a new DFS, but the new DFS that we will start in a minute is going to do just this vertex. So we will put the discrete math at the top. So we can find the topological sort by doing DFS and placing the vertices at the bottom of the list as we finish them. So we can write this code as just, this is topological sort 1, topological sort 1 of G, and this is topological sort 2 of G. So basically do DFS, and whenever a vertex U is finished, do S dot add to head or add to tail. So when we put at the bottom of the list. OK, so we put, at some point we had this in the list. So when we added OS, did we add it to the top or to the tail, to the head or to the tail? Head. We added it to the head. So add to head of U. And that's it. And since this operation is not going to add anything to the asymptotic complexity of DFS, so this is going to be only theta of V plus E. OK? So now we have two algorithms for doing topological sort. Both of them are V plus E. So asymptotically, this code is equivalent, does the same thing as this code. But which one is expected to take more time, more actual time? Well, here definitely we're doing more operations. So asymptotically they're the same. But in terms of expected actual running time, not asymptotic time, actual running time. This is expected to take more time because we're doing lots of extra operations here. So if you remember the code for DFS, we only have one V plus E loop, but here we have two V plus E loops. We have two of them. So there is more work. We expect this to take more time. So this is a very good application of DFS. And so far we have seen two interesting applications of DFS: detecting cycles in the graph and doing topological sort. So DFS is a good algorithm for studying the structure of the graph and giving us information about the structure and the relations among vertices and edges, and like detecting cycles or finding a topological sort. So these are things that we cannot do with BFS. Yes?
So that only worked because you chose a good source. How did you know to choose that source?
No, in fact, it will work with any source.
Oh.
So do you want to do it? What source do you suggest?
Well, if you chose like a bad source, like
Okay, what is bad for you? Give me a bad source and we will get correct results.
OS.
So let's OS?
Yeah.
Okay, so we have like 2 minutes. Okay, so OS is a bad source. So this is 1. So we will visit security. So this is going to be 2. So now it's time to finish security. So it's going to be 3. So we'll put security at the bottom of the list. Then we go back to the OS, and we are done with this source, right? So we have to pick another source. So give me another bad source.
Software engineering.
Okay, so software engineering is another bad source. So this is this is going to be 4. Oh, sorry. When we finish this as 4, so we put OS. Then software engineering is going to be we'll give it 5, but it doesn't have any dependence. So we'll finish it and we'll put software engineering. Okay, so it's giving a different solution, but it's still valid because whenever we put a vertex, we know that everything that depends on it, if any, has been already placed beneath it. Okay, so another bad source is algorithms, maybe 7, and we just okay. So if we pick this, for example, the second source is going to be this. So if we do this as 7, then we'll go 7, 8, and then it will recognize that this is visited, this is visited. It will go to algorithms because it hasn't been visited. So this is number 9. Then this is so we'll do this 10. Then we'll put algorithm.